In this first chapter, we'll show the role of the materials for the green and digital transition. I'm Alex Nominé, professor at the University of Lorraine and Jožef Stefan Institute in Slovenia, and I'm very happy to have you here for a few minutes. We speak about materials for the green and digital transition, and that might surprise you at this stage. But let's speak first about the energy transitions. In this first chart, you see the evolution of the percentage of energy used by humanity depending on the energy source. In blue, you see the oil, the coal in red, the gas in green, and the other one represents what we call the renewable energies or the nuclear energy. If you look at this graph, you may think that an energy transition started in the 70s because the proportion of the fossil energy slightly decreased. Is that true? Unfortunately not. The proportion of fossil energy has decreased indeed, but the total consumption of energy by humanity has increased exponentially. Therefore, the consumption of oil, of gas, of coal has increased over the time. Therefore, we cannot say that any transition happened in the past, which means that what we have to do in the three upcoming decades is unprecedented in the human history. It's actually a matter of energy transformations. Let's start with very basic things. On Earth, at room temperature and at atmospheric pressure, the most stable molecule with carbon and oxygen is CO2. To be sure of that, let's imagine you have pure carbon and you have pure oxygen. You know that if you bring a spark, which is an activation energy, you will trigger a combustion reaction, in other terms, fire. And this reaction is exothermal because the system will give you some energy, which is heat, because the carbon and oxygen are less stable than CO2. So the reverse reaction is possible indeed. We could break the CO2 and create back carbon and oxygen, but this will cost us energy. So if you look in the full cycle of the fossils, actually the Earth does that for millions of years, because CO2 was present in the atmosphere of the Earth, and under the effect of the sunlight, it could be transformed into organic matter. Organic means containing carbon. This is called the photosynthesis, and it's a transformation of photoenergy, energy from the light, into chemical energy, because the CO2 was transformed into carbon-based material, which is higher in chemical energy, as we show in the previous slide. Under some circumstances, this organic matter can be trapped in the soil, and after years and years, under high pressure and high temperature, it can be converted into fossils, such as oil, gas, or coal. But this takes few tens or hundreds of millions of years. And this is what we are extracting now for 1 or 2 centuries maximum. We are extracting very actively something that took millions of years to be produced. This oil, gas, fossils is just chemical energy that is trapped in the soils. And this chemical energy is coming from photoenergy, from the sunlight transforming into organic matter. And now we use these fossils for different things. We use it for heating. This is a conversion from chemical energy to thermal energy. We use it for transportation, in our car, for example. It's a transformation of this chemical energy into thermal energy, into then mechanical energy, a movement. And this movement can also be used in power plants to be transformed into electricity. So you understand at this stage that it's only a matter of transformation of energy. Let's have a look at the renewables now. What renewable energy do we have available on Earth? The sun is bringing us photoenergy. The wind is a movement of matter, of air. This is mechanical energy. But we also have water streams, like a cascade to make it simple. It's also mechanical energy. But this energy, we can hardly use it for our nowadays usage. We need energy harvesting system. We have solar cells that can convert the sunlight into energy, the wind turbine, or the dam. Once we have this electrical energy, so that this photoenergy or mechanical energy is transformed into electric energy, this has to be transported, or this has to be stored. Because indeed, when we have a sun, we don't necessarily need to switch on the light. So we need to store this energy for further usage. And this is much harder to store electricity than to store oil. So this is why we will need batteries or possibly hydrogen to store the energy for further usage, which can be thermal energy for heating, which can be again photoenergy for our houses, or which can be mechanical energies for our car. It's only a matter of transforming the energy. Let's have a look at the energy transformation in the context of the green and digital transition. Let's start with the transformation from mechanical energy to electric energy and vice versa. The physics concept is rather old and has been formalized by James Clerk Maxwell in the 19th century. It's called the Maxwell equation. In a short term, what does it mean? It means that in one of the equations you can see that there is a possibility to transform an electric field into a variation of magnetic field and vice versa. At this stage, you may wonder, why is that interesting for green and digital transition? The one who made something useful out of this equation is Nikola Tesla, a Serbian physicist from the late 19th century and early 20th century. He actually understood that if a magnet moves between coils, this is going to generate a current. Or if you generate a current into a coil, you can make the magnet move. This is the birth of the alternator, who is used for wind turbines or for dam, or of the electrical motor that we use for car. This is the way to transfer electricity into mechanical energy or mechanical energy into electricity. Let's have a look now at one of Tesla's invention. This is a very simple flashlight that you can find in any shop. Well, look, if I turn this, I make a mechanical energy. And this mechanical energy will generate electricity thanks to this device here, which is an alternator. So the mechanical energy was transformed into electrical energy, which was transformed into light energy. But with electricity, we can do other transformation of energy. Look, let's connect this device to a small electric car with an electric motor. The mechanical energy I generated here has been here transformed into electricity. Part of it became light. Another part of it went to the motor and generate another mechanical energy. Let's have a look now at a more practical example. This is a wind turbine, as you recognize. And here, let's imagine the wind will generate a mechanical energy, which will generate movement, and this will generate electricity, which here switch on the light. So let's have a look at what is inside this wind turbine. So the wind will push on these blades and generate a circular movement of this gray device. Let's have a look what it is. This is actually a magnet. Look. So here, the wind generates the rotation of the magnet. And on the other side of the device, we have other coils. From these coils, the electrons will be extracted. In other terms, the electricity will be generated and will go outside of the wind turbine. So to summarize and come back to the topic of our course, we have seen now that for transferring mechanical energy to electrical energy and vice versa, we need conducting materials, for example, copper and aluminum, and we need magnets. And magnets can be iron. This is the simplest one. This is the one that you have on your fridge, for example. But we need more powerful one, which will be based on rare earth element, such as neodymium, praseodymium, terbium, samarium, or other metals like cobalt or nickel. Let's switch now to another energy transformation, from the light to electricity, from photoenergy to electric energy, and vice versa. Another great scientist come at stage now. It's Albert Einstein. He got the Nobel Prize in 1921 for a major discovery made 16 years before, in 1905. He discovered the photoelectric effect. The fact that photon, a grain of light, can be transformed into an electron, a grain of electricity, if these photons are meeting a semiconductor material. There is much physics behind that. You can discover more in our book, but the applicable discovery was made a few decades later, simultaneously in the USA and the USSR, when it has been discovered that when taking two semiconductors, you can then control this flow of electrons, meaning this flow of electricity. This is the p-n junction. This is used in transistors, but even more important, this is used in solar cells. So now, this is a solar cell. So if I bring some light from my phone on the solar cell, see what happens? The small LEDs are switching on. This is actually a funny story, because here is made of semiconductor, the solar cell is made of semiconductor, to create a current, and here with the LED, you have the exact opposite. The current generates light. Let's look a little bit further into this solar cell. Here you have some grayish blue, dark blue material. This is the silicon. You can even see the grain of the matter. And you can see this is the semiconductor is responsible for the transformation of photon into electron. And here you have some metallic cables. Usually it's made of silver. They are used to extract the electrons and to transport the electricity to here. And then the electricity can be used for whatever you want. So as we discussed, the main semiconductor is silicon, but there are many other ones. There is also gallium arsenide, cadmium tellurium, gallium phosphide. So you have different metals possible for solar cell. Of course, the most used is silicon, because silicon is abundant and relatively cheap compared to the other metals. But you also need to gather and extract these electrons, and for that you need conductive materials such as silver, for example. Now, if we speak about storing energy, electricity, it is absolutely crucial to understand the transfer from electric energy to chemical energy and vice versa. The most popular example is the batteries. So batteries is based on a redox reaction. So you have an anode and a cathode. Both of them have the ability to store charge carriers. In this case, it's an ion. An ion is an atom to which an electron has withdrawn. Therefore, they carry a positive charge. These ions can be stored at the anode during the charging and then come back to their usual place, which is at the cathode, in another material that is usually taking them. So you are withdrawing lithium ions from the cathode. The matter doesn't like it because you make the energy rise. You force this process to happen during the charge. And when you use it, the lithium comes back to the cathode. On the opposite side, since there is a flow of lithium in the battery, there will be a flow of electron on the circuit. This is these electrons that you use in your smartphone or that you use in your cars. This generates current, and current with a voltage means power. A battery, as we saw, is composed of an anode and a cathode. The anodes are currently made of graphite, which is carbon. In the future, they may be made out of silicon, but today the performance are not yet as good as expected. But perhaps in the future, this is going to be better. For the cathodes, we have three main chemistry of batteries for the car industry. This is lithium plus nickel, manganese, and cobalt. For the NMC battery, you have lithium, iron, phosphorus for the LFP battery. Or you have nickel, cobalt, aluminum, and lithium for NCA batteries.
For lithium-ion batteries, we need, for NMC batteries, lithium, nickel, manganese, and cobalt. Cobalt is certainly one of the most critical elements in this series of metals because it is hosted at more than 70% in Congo. Here you have heterogenite, which is a cobalt oxyhydroxide, which constitutes the main ore in the oxidized part of these deposits. This is typically the ores which are exploited both by families in Africa, in Congo, and also by big mining companies. Of course, there is a monopoly of cobalt by Congo, but there are still other sources, as 30% of the remaining ores are located in other countries with different types of ores, such as the cobalt in laterites. It is the case of now Indonesia and Philippines, which are exploited cobalt together with nickel, and it is also the case in New Caledonia, in the Godo deposit, where both elements are exploited. So it's typical example of co-valorization. What you see here is a granite. Granite, you know, this kind of rock because you find it frequently in the pavement of the sidewalks. But this granite is quite exceptional. It comes from Échassières, Beauvoir, in the Massif Central in France. And this is a leucogranite, that means it is very whitish. And it is composed mostly of quartz and two feldspars, as many other granites. But it contains what you see, the small platelets shining here when moving the sample. And these small platelets contain lithium and rubidium and cesium. So this could be exploited for lithium, especially for making then lithium batteries. But these granites contains also a lot of metals, such as tin, niobium, and tantalum, which could be exploited as co-product.
In your phone or in other devices, you may have different chemistry of battery. Most of them are still based on lithium, but perhaps with a different composition. The three batteries I was talking about are mostly for the car industry. In the future, it might be that we will substitute lithium by sodium. There is active research on that. Today it's not in the market, but nobody knows the future. It shouldn't also not be forgot that there is also a need for contacts. And these contacts can be made of aluminum and copper. And this shows you that the car industry will generate an important demand in those materials. Let's speak about the hydrogen now. You know this graph. We saw it at the beginning of the class, but it was with CO2. Actually, the same things can be said about the water. As you know, water is a very stable molecule. We have it everywhere on Earth. But if we want to create molecule, we have to break this very stable molecule, so we need to bring energy. If we want to create out of water, H2, the hydrogen, with oxygen. To make it simpler, we need to make the energy barrier smaller, as described in this sketch. And for that, we need catalysts. Catalysts are metals that accelerate a reaction by decreasing the energy barriers. These metals are quite often rare. Most of them are in the family of platinum. You know, platinum is an extremely rare material and quite expensive. So you have other metals of this family that works, like iridium, ruthenium, palladium. But iridium and ruthenium, for example, are even rarer than platinum. This is why researchers look for alternative catalysts based on titanium for photocatalysis, or manganese-based, cobalt-based, iron-based, or sometimes rare earth-based materials. Let's come now to our conclusion. As an introduction, I hope that I convinced you that green and digital transition are absolutely needed, but they will be extremely intensive in terms of metal resource. Metal extraction, consumption, recycling must be integrated today in our planning for sustainable and digital transformation. And let's not forget that fossils are not renewable, but the metals needed to collect the renewable energy are not renewable either. This is why we should be very wise and very careful in our usage of them. Thank you very much for your attention. Enjoy reading our book and enjoy the next videos.